So moving on to question number 14, we're going to calculate compound interest. And so we're going to continue using our exponential formula. So 14, an advertisement indicated that a 3-year certificate of deposit, so that's when you put money into this, it's called a CD for 3 years. It's going to earn 1% of interest, and then you're going to get more money back at the end of the 3-year period. It's going to yield 4.533%. Let's start there. 4.53%. You have to move this 2 to the left. 1 would get it before the 4. 1 more adds another 0. So this is 0.0453 when we're dealing with this as a percent. And so we invested $2,000. What's it going to be worth after 3 years? So when we start this out, you start with the number that you began with, which is 2,000 times. Now it's 1 plus, because we're earning money, 0.0453. So we're 100% is what you started with, plus 4.53%. So altogether, it's 1.0453, and it's raised to the amount of years, which is 3. So we're just going to go ahead and run this through the calculator. So we have $2,284.29. Then we're not going to round that up. The bank isn't going to give you extra money, so it's always going to be just the minimal amount there. So let's go to 15. When Bree was born, she received a gift of $500, so that's what we're starting with. Hers is in an account 5.2%. So again, 5.2%, move it 2 spots, 1 in front of the 5, 1 more, adds a 0. So 0.052. Now, this would be a mistake if I left it like this. This would actually take 5.2%. We want to add 5.2%, which means we need the 1 there because it's actually 1 plus 0.052. So 1.052 will make it grow, and it's over 12 years. So 500 times 1.052 raised to the 12th. And she now has $918.66. Okay. After number 15, we jumped to 18, which is this chart. So in 1990, there's 4.4 million cell phone subscribers. By 2006, there was 219.4 million. The table below shows that number. Now, let's take a look at those numbers and the numbers that we see on the chart. It says in 1990, there's 4.4 million. This says 4,369. But they're representing the same number because this is the cell phone subscribers in thousands. So if I took that number, 4,369, but that's in thousands, meaning I have to add 3 zeros to it in thousands. Now take a look at it. This is 4,369,000, which they called 4.4 million. And then our last number, 219,420, that's in thousands. So we got to move that decimal 3 spots to the right. Okay, and then you can see they said 219.4 million. That's what this is, 219.4 million. All right, so we're going to have to make sure we're careful with those numbers and realize that this is not actually 4,000, this is 4 million, so on and so forth as we go through this data. So we're going to leave the numbers small for now, but in the end, when we actually come up with an answer to something, we got to make sure that we're moving that decimal 3 spots to represent the thousands. Okay, so part A, we're going to create that scatter plot. And for the sake of time, I already input these. So remember, you're going to hit Stat and Edit, and you're going to input these into L1, L2. We're not going to put the actual year in. You'll see that that will create an error when you go try and create the equation because these numbers are just too big. Okay, the equation is going to get out of control too fast. So we start with year 0, and we go 1, 2, 3, 4. We'd go all the way up to 16 numbers here. There are 17 numbers altogether, and so students get confused, but year 1990 is going to be 0. So we're actually only going to get up to 16 because we're not starting with 1, we're starting with 0. Okay, so now if I want to graph this, before I go ahead and try and look at the graph, I'm going to go adjust my window because clearly this is not going to be a perfect window here. I'm starting with year 0. So I'm going to start at 0. And I'm going all the way up to what I said, 16. So I'm going to go to 20. And counting by ones is just fine. Now here's the important part. Okay, if I want to see this, I got to have a minimum of something close to 4,000. So I'm just going to go with 4,000 for my y's. And my maximum's got to be above 219,000. So I'm going to go 220,000. And now that's a massive jump. So my scale, I'm going to count by 10,000s. Now, if I go to graph, I don't see anything. And you may think something's wrong, but you got to always remember to turn your plot on. So go to your y equals. There we go. Go to your y equals. Turn your plot on, hit enter. Now that your plot's on and you go to graph, you'll see it. Okay, so make a scatter plot. We can see that this is curving up, something along those lines. And you can see, to answer the question, why is an exponential model a better model for this data than a linear model? Okay, and I would just say the data curves at an exponential rate. Okay, it's not a straight line, it's curving up. That's a good answer there. Okay, letter B. Use regression to find an equation. So we're going to hit stat. We're going to go to calculate, and it's 0. If you scroll all the way down, we don't want a linear equation, we want an exponential. So it's number 0, exponential regression. Go down to calculate. It runs the numbers for you. So it's a times b to the x. It's 5, 8, 8, 1. Point. We'll go 2 spots. 3, 3 times 1.29. You got a bunch of zeros there, so we'll leave it right there. Raised to the x. So there's your good equation for part B. And now part C, we got to actually answer the question. So using our equation, predict the number of cell phone subscribers in the year 2013. So 2013, we cannot input that into this because we didn't actually count by the years themselves. We started with 0 and counted away from 1990. So if you go ahead and subtract 2013 and 1990, you'll find out how many years have passed, and that's 23. So we are going to plug 23 into this equation. So I'm going to go back to my main screen. And now, going back to what I was talking about earlier, I got to remember that this number is being expressed in thousands. Okay, so just like up here when we had 4,369, but it actually was 4.4 million because we had to move that decimal 3 spots. We had to move the decimal 3 spots because the data was given to us in thousands. We would have to do the same thing here. Okay, so we're going to have to move that decimal 3 spots, which conveniently puts it right at the end there. So this is just one big number. If I left it like this, where the decimal is right now, I would have to say this thousands. Okay, so for the sake of just making a nice number that we can understand, we're going to just move that decimal 3 spots. And we get our answer right there. So 2,056,074,681. Jump into number 20. So now we have depreciation. We're still going to use the same formula, but instead of adding to 100%, we're taking away from 100%. So our starting point here was 22,000, price of a car. Price needs to go down, so we need to be multiplying by a number less than 1. So it's 1 minus the percent that it's decreasing by. It's going down by 20%. Move that decimal 2 spots. That's 0.2. So 1 minus 0.2. It's 0.8. It's 100% minus 20%. So that's 80%. And again, this comes from what's the car worth now after 1 year? 80% of what it used to be because it's 20% less, depreciated 20% from 100%. And so the growth factor for this is going to be 0.8. So when we go to answer the questions, they're starting you off with what's just the growth factor, 0.8. B, what's the car's value 1 year after purchase? So we're going to go ahead and run this equation with a 1 up here, which doesn't change much. So basically, after 1 year, it's worth 80% of what it was. We don't need to raise this to the first because it doesn't change anything. So it's going to be 17,600. And then what's the value after n years of purchase? So they're basically just asking you for the equation because they're giving you a variable for time. And so we're going to put the n up there where x normally goes. All right, 21 to 24. Does the equation describe a situation of constant increase? That would be a line with a positive slope. Constant decrease, a line with a negative slope. Exponential growth, so an exponential equation with a growth factor more than 1. Or exponential decay, that's an exponential equation with a growth factor less than 1. So we can run through this real quick. First one, that's y equals mx plus b. That is a line, which means it's constant something. And you have to look at the slope, not the intercept. Doesn't matter where it hits the y-axis, it's the slope. It's positive. Doesn't matter that it's a fraction. It's positive. This is going to be going up. This is a constant increase. 22, y equals mx plus b. This is a line. This is constant. Take a look at the slope. It's negative. This is down 3 over 1, down 3 over 1. So while it's a line and it's constant, it is decreasing. 23. This is exponential something. And if we jump ahead to 24, this is also exponential. And so we just need to tell the difference between exponential growth and exponential decay. It's all about the growth factor, which is the number being raised to the exponent. If it's more than 1, it's growth. Okay, right here, this is 3 is more than 1. So that is growth. That is going to increase. And right here, our growth factor, you notice they just switched the place of the numbers. Okay, same numbers, different places. The growth factor here is less than 1. And so this is going to be decay. Okay, 27. We're going to compare some linear increase with exponential growth. So country A has 10 million people. Its population is growing by 2%. So 10 million people increasing. So it's 1 plus 2%, 0.02. So that's 1.02 raised to however much. And as I look down, give an equation for the population country A in n years. So I put x. So n years, it just means use n instead of x. This is letter A. Letter B now is going to be the linear function. So country B has 20 million people, and it's growing by 1 million every single year. That's a slope, up 1 million every single. So I am starting with 20 million. And I'm just increasing it by a constant rate, so I'm not multiplying. This is y equals mx plus b. The slope is 1 million positive times the number of years. So if it's 1 year, it's just 20 million plus 1 million. If it's 2 years, you would do 2 times a million and add it to the 20. 3 years, 3 times a million. Okay, every year is that million. Okay, part C now. In 30 years, which country would have the greater population? So we're going to go ahead and run both of these numbers with a 30 in it. So starting with A, taking 10 million times 1.02 raised to the 30 for 30 years later. So this one, 1.8113615. About 18 million. So clearly I'm going to stop right there. This one started at 20 and it's going to be growing. After 30 years, well, that just tells you right there, there's going to be another 30 million attached to it. So that would be 50 million. I don't even have to run the numbers. You would put 30 in. 30 times a million is 30 million plus the 20 million is 50 million. So to answer the question, which country has the greater population? It's country B. Explain why. You would just kind of go through your math here. Started with 20 mil. Country A is only at 18 mil. Okay, because it started with more and it grew, it's going to have more. But eventually, exponential growth always overtakes linear growth. So what about 100 years? So let's go ahead and run this now. So 10 million, 1, 2, 3, 1, 2, 3, times 1.02. But now let's raise it to 100. 100 years later. Country A, 724464661. We're at 72 million. Country B, we're going to do a million times 100, and then add the 20 million that we started with. So how many zeros? 1, 2, 3, 4, 5, 6, 7. And so even 100 years in here, okay, country B is still the answer. Country B still has more. It's 120 million to 72 million. Now, like I said, eventually exponential growth will overtake this, but it's going to take a long time because it's only 2% growth. If this was 20% growth, it would have already overtaken it. So 2% is a small percentage of growth, but eventually this number gets big enough that 2% of it, 2% of it, 2% of it is going to grow it just as faster than this. Because right now this is growing by 1 million. If I take 2% of this, okay, that's going to be more than 1 million. And so it's going to be growing a little bit faster, but it's going to take a while to catch country B. So just comparing linear growth to exponential growth, if they had started at the same amount, it definitely would have gotten to it faster. But since the linear growth started with more, it's going to take it just a little bit longer because it's a 2% growth. So just looking at the two different types of growth there. Okay, jumping to 38, which is the graph of this function. So when I take a look at this, I see this is exponential, so it should be curving, and my growth factor is less than 1. So this should be decay, so it should be going down. So right away, if I had these listed out, A, B, C, D. First of all, D, that's incorrect completely. Letter B shows growth. This is not growth. So right away, I'm down to A and C. Now they're both decay, and so I have to think carefully here about what's going on. This one is hitting somewhere up in the positives. This one is hitting at 0 and then is going to end up over here somewhere. So what I should do is probably just try some different things. So let's say x was a positive number. This one is going to give me a positive answer when x is positive. When x is positive here, it's going to give me a negative. So this is one way to think about it. So I'm going to go ahead and take my 1/3 alpha x and raise it to a positive number. So let's just raise it to the positive 5. Now you notice this is a super small number that I get, okay, but it is not negative. So that should eliminate letter C. It's just going to be a super small number getting closer and closer to 0. What I also should test, besides just some random positive number, is the number that I can see clearly. When x is 0, it's either going to be a positive number or it's going to be 0 because this is hitting at 0, 0. So what does it look like when I actually raise this to the 0 power? Because, oops, that's what this is showing right here at x equals 0. So raising it to the 0. And think about it for a second. We know that, right? Anything raised to the 0 is 1. So it shouldn't be hitting at 0. Anything raised to the 0 power when x is 0, we should be up here at 1. And so letter A would be the correct answer here. Okay, going over to 39. We're going to basically interpret some functional data here from the graph. And we got to be able to understand our function notation. That's what I was going for there. Okay, so what is the value of L of 2? So when it's written in function notation, the x is in the parentheses here, L of x. Okay, so the number that you see here when they're asking this question is the number going in for x. So what we've got to do is go find our x values and go to 2 and see what is the value of the function. So here's 2, and go up. Now when you see this, you got to realize the 2 is the x, the 1 here is the y, and that's what we're looking for. So the answer here, when x is 2, the value of the function is 1. Letter B, what's the value of L of 0? So again, that's the x spot. So when x is 0, the function is at 2. Letter C, what's the domain? So domain are all the possible x values. Now, this does not have arrows on it. It doesn't go on forever. It stops here, and it stops here. So the lowest number is 0, and the highest number is 4 in terms of our x's. And everything in between is included. If these were just dots, you would just list the x values, but they're connected. So every fraction and decimal between them is included. So we have to write this as an inequality. So the smallest number is 0, x is greater than or equal to 0, but also less than or equal to 4. Same idea with the range. All of our possible y values. I have a y value of 2, of 1, of 0, and everything in between is included. These are not just single points. They're connected. All the fractions and decimals between 0 and 1 and 2 are accounted for. So we're going from 0, and we're going up to 2. So last but not least, number 40. Looking at the graph, what is f of 0? Again, this is your x value. So you're going to go where x is 0. Find out what's the y value, what's the value of the function. So that is 3. What's f of 3? So we're going to go to where x is 3. 1, 2, 3. It looks like it's hitting right on that spot right there. So that's when y is 0. What's the domain? So my x values. Now this is different because it has arrows. This is going up, but it's also moving slowly to the right and slowly to the left. And if it's going to continue forever, even though it's going slowly, it will cover every x value to the left, every x value to the right, both ways. Everything in between. Not going to ever miss an x value here. So this is an all real number situation. There's no limit to this. It's going to hit every x in both directions. And letter D, what's the range? So it's going to go forever in this direction. It will hit every y up in the positive realm, but it's not going to hit every negative. It's going to hit -1, and it never hits -2. It even doesn't hit any of the decimals past -1. So -1 is going to be the smallest number, and then everything above it greater than -1 is part of it. So you're going to say y is greater than or equal to